then you have the same Gaussian behavior for all kind of matrices that you have, with dependent elements, independent elements, any kind of distribution with enough finite moments. You obtain something like that. That is for Hermitian case. If you have, for example, orthogonal case, so real symmetric matrices, then you get same, not the same behavior, but it's behavior which you obtain if you compute this thing for Gaussian orthogonal ensemble. But again, the behavior will be the same as for most simple case, which is Gaussian case. And this question is closely related to localization and delocalization, because that is kind of behavior that you expect to have for delocalization. For localization, you expect to have Poisson statistics. And from the matrices point of view, that is the most natural question that you actually can ask about local regime. But generally, random matrix people typically have delocalization, because almost all classical ensembles of random matrices that we have and that already studied have delocalized eigenvectors, and so they have such kind of statistics like that. So it's about Wagner matrices, so matrices with independent, Hermitian matrices with independent elements. It's about beta ensembles, which come with different beta sample covariance matrices and many other matrices. Mainly so almost all matrices that are studied, they have delocalized eigenvector, and so that statistics that comes from Wigner-Dystron distribution. From the other side of that picture, we have a famous random Schrödinger operators, or models that you can define like Laplacian plus some potential, but in one simplest 1D case, what you have is such kind of matrices, and here V is IAD elements. From that point of view, you can say that that matrix is somehow also random matrices, but with some non-random stuff inside. And for this matrices, which that is known for many years, we have localization and Poisson-Lochtov spectral statistics that was proved first by Felix Spencer, then by Asman Molchanov, and by some other peoples. But you probably know that in other dimension it's still unknown, and so there are some conjecture, but it's still unknown and hardly accessible actually at that point. So you can see that from one point we have standard random matrix ensembles. From another side we have random Schrödinger operator, which has a spatial structure like that. We are going to speak about random band matrices, which somehow an intermediate model between these two cases. So there is a general definition that you can see. You have some kind of box in ZD, so you can define it in any dimension. The matrix is Hermitian, and you consider some kind of band profile, which is some function which has typically compact support or rapid decay, and then the dispersion of your elements is defined by this matrix J. But let me show you in the simplest case 1D when I'm going to speak about. The matrix looks like that. You have kind of band here, which has random elements with some, it depends on your J, but that can be fixed variance, or it can be rapid decay, and all other elements, again, it's 0 if your J have a compact support, or it can be rapid decay dispersion like that. But anyway, the main thing here is that all dispersions that are not small should be in a band of size W, and this W is the main parameter that we are going to play with, and it's so this W can be from 1 to n. Certainly you can look on this matrix in any dimensional, but the picture will be the same. So the dispersion is fixed or non-zero, not small, if your elements are close to each other, the distance between them not smaller than W. So you can see that that matrix also has a spatial structure, and you can see that Vara in W, you can see somehow, so if W equal to n, you have a Wagner matrices. If W equal to 1, you don't have Schrödinger because there is no fixed part, you don't have Laplacian here, but you have something like that. Okay, so the most interesting thing here that although that matrix are more simple generally than random Schrödinger, you also can see that kind of crossovers and phase transition we expect to have in there. So what is the conjecture about the transition? So Vara in W, again, fixed W means that we close to random Schrödinger behavior, W Wagner matrices, and so Gaussian behaviors like that. And the conjecture is the following, that in dimensional 1, localization length is W square, which, if we speak about random matrices, means the following. If W, so the white...
sorry, what is the dimension in terms of matrices?
N times n. And big is the dimension of matrix. D, that means not the dimensional of matrix, that means the dimensional of the box that you have here. So from what...
J don't necessarily belong to integers, they could belong to a higher dimensional value.
Yeah. Yeah, so if you have dimensional 1, that means that if your bandwidth grows faster than square root of n, then you have the same as for random matrices, Wagner matrices, so GUE statistics. If W is smaller than square root of n, then you have localization and Poisson statistics. In dimensional 2, you have, it's expected that your localization length is quite big, so it's e to W square, which means again that if W is bigger than square root of log, then you have delocalization. If W is smaller than log, square root of log, you have localization. And in D equals 3, you expect to have delocalization if only W bigger than some constant, and that's should be quite a small constant. The interesting thing is that all these conjectures are in correspondence with the conjecture for random Schrödinger with a proper lambda that we choose. And it seems that random matrices should be much more accessible than random Schrödinger. Unfortunately, they're probably much more accessible, but still hard. So we don't know much, especially in D1 and D equals 3. We don't know much about, we don't know actually anything about delocalization and localization. But in D equal 1, we can say something, and that is what I'm going to mainly speak about. Okay, so let me first say what kind of existing results we have. So, as I told, we have the results only in D equal 1. And what we have that from the work of Schenker, that localization length is smaller than W to the 8. Once again, that is 1D case. The expected value is W square. Yes, so that bound are far from the optimal. And that bound was obtained by localization technique that was used for random Schrödinger, and it's not much improved, so now it's improved to W to the 7, but it's still far from W squared. From the random matrix point of view, there are some results from other side. They comes with random matrix methods, and that proves, since we know the universality for Wagner matrices, for W equal n, we know that localization length is bigger than W, and in the work of Borghetti-Ardashiaou was even proved that gap universality for W of order n, so n over half, n over 3, for example, and so on. So not the whole matrix, but again, we interested in the regime n W of order square root of n or bigger than square root of n, so not just n. So the main problem here is to control the resolvent of matrix that you have up to the order, so you want to consider such kind of resolvent, and you're interested in the imaginary part of Z of order 1 over n. The technique which comes from the random matrix method, so from Ardashiaou approach, they really allows you to control only epsilon of order 1 over W. That gives you such information about localization length, but not to optimal scale. So for example, there are some results which prove that localization length is bigger than W to 7/6 and then 5/4. But again, we need W squared. But even these results, they are not it's a not strong localization because they hold only for most eigenfunction, not for all, but with for big part, but not for all eigenvalues.
So do the last two results, are they able to make epsilon smaller than 1/W?
No.
No.
Yes.
But nevertheless, they can still get information.
Some information, yes, but that is weak form, so it's not actually a strong form of localization. So they can prove some kind of bounds on probability that we have localization, but that is not really deal with this problem of epsilon 1/n.
So as far as you know, these techniques that have been developed?
Here, no. So the technique that they use here potentially can break this barrier, but still it's hard to predict.
They have not been able to break
yes.
the epsilon.
Yeah, so it's different. The technique of this paper is different from the technique of that paper, and in principle, I think it can somehow, it's possible. There's no such a problem. So there are lots of technical problems there as well, but not that problem that they have here. So probably at some point it's possible to extend it to another, to another scale. But at this point, they don't know how to do this, even with this technique that they have. But previously they wasn't able even to do, for example, for 2 blocks. That model that you have just n over,
so they can do that.
Yes, something like that, and they can do. So now, for example, they can do strong universality, so gap probability and other stuff, gap universality for example, W equal to n over 2. Previously, they wasn't able to do this with the technique that they have here. Okay, so another method which allows to work with the random operators with non-trivial spatial structure is so-called supersymmetry technique. I'm not going to tell much about this here, but that is technique which based on representation of the determinant as an integral over some formal Grassmann variables, so anti-commuting variables. It's technique that allows you to obtain the convenient integral representation for main spectral characteristics such as green function, density of states, correlation function, determinants, or some other stuff like that. And the representation that you can get using that technique is somehow an average of certain observables in some kind of statistical mechanics model. I'll show a little bit later how this model looks like. And to obtain this integral representation is mainly algebraic step, and typically that is few-page computation. The main problem is that you need to deal with what you get after this technique. So you obtain some kind of integral representation to analyze it rigorously.
But you should emphasize the intervals are big, right?
Yes. I will show that it's not like these integrals, they're huge, they really quite complicated, so you need to deal with analysis of that kind of integral. And the main point that sometimes they don't have sometimes they have only complex variable, but sometimes they also still have anti-commuting variables, even in the simplest form. And so you need to analyze some kind of formal integrals over anti-commuting variables, which can be hard. So, but previously, before I show you what kind of integral representation you can get, I want to say a few words about the technique. So, first of all, that technique mostly used for only Gaussian elements. So you can't consider any other distribution, except the case of characteristic polynomials that we discuss later. But in general, that is not such a big deal, because first of all, we don't know nothing even with Gaussian elements. And second, there are now such technique which comes from Erdős-Yaró approach, which allows you, if you know something for Gaussian matrices and you have strong bounds, there is a standard approach now which allows you to obtain the same thing for the distribution with 4 Gaussian moments. So in principle, you can generalize it to a more general distribution after you did it with you do this with Gaussian bands. And second step, again, it's not because of the technique, supersymmetric technique. It's because the integral that you have is such hard that sometimes it's more simple to analyze it with some specific covariance that you take. And now I want to show you two types of specific models that I'm going to consider. The first model is that random band matrices that we have previously, but the covariance of, so J is the covariance of element xij that we have in matrix, and we're going to consider it in this specific way. So you can see that the covariance, if difference between I and j is like a constant, you have the covariance of order 1 over w. If the difference between I and j bigger than w, you have exponential decay. Yeah, so that is really, you have a band of elements with covariance 1 over w, and then you have a rapid decay of the elements that you have. So that is really the band matrices. And second matrices that I'm going to consider is so-called block band matrices. They connected to electron orbitals, and so sometimes it's called Wagner orbital model elements, and dispersion 1 over 2 alpha over w, and bj are just independent w times w Genibri matrices, which means that they have all independent Gaussian elements with dispersion alpha over w. That is what we have. So again, we have the dispersion 1 over 2 alpha in all A's, and we have dispersion alpha over w in all B's. That's
so the idea is, I mean, in this parameterization, it looks like the diagonal is dominant because of the, you've got the alpha over.
Yeah, but alpha somehow is fixed. Yes, you need some kind of positivity here, but again, you can see that dispersion in A and B are all of order 1 over w. So you have some kind of, again, band structure. So your band is of order 2w plus 1 actually here. But again, that is that specific form of covariance, it comes from the Soucy techniques that you need to obtain the integral representation. So in principle, you can obtain integral representation for any covariance, but for these two particular covariants, it's much simpler to analyze what you get.
Could you say in a couple words how this is related to orbitals?
So assume that you have, so if you have some box and electrons there, you assign to each electron one vector of size w, and the covariance of these two vectors, that is your block w times w that you have. So you organize the covariance of all these orbitals in big matrix, and each matrix is actually the covariance of two vectors that you have. Yeah, so that is how it obtained. So I don't want to name it Wagner model, because Wagner model sometimes people think about that as a model which has which more looks like random Schrödinger because it has some non-random parts. That's why I call it block band matrices. But in principle, it's also looks like that. So we mainly will consider just this case because I'm going to consider only 1D case, and with this 3 diagonal. Okay, so now what I want to say, I want to write what is generalized correlation function. So you can see that I consider the ratio of the determinant, so just 2 determinant on 2 divided by 2 determinant, and here Z is some kind of energy that we take. Probably I have to say that for all band matrices with W goes to infinity, the density of states is a standard Wagner semicircular law, so the spectrum is minus 2, 2. So I'm going to speak about the bulk of the spectrum, so I'm interested only in the energies which lies between minus 2 and 2. Okay, so what we get here is just this kind of ratio of the determinant. As I told you, to obtain integral representation, I use supersymmetry technique, which based on representation of the determinants. So I need the determinants. And how it's related to the density of states or to the correlation function, you may see that if we take the derivative of this guy over z1 and put z1 equal to z1 prime, we get the trace of resolvent, which is the imaginary part of which gives the density of states. And similarly, if you differentiate this guy by z1 prime, z2 prime, and put then equal z1, you obtain part of second correlation function. So if you can obtain integral representation for this kind of thing, then after taking some derivative, you can obtain integral representation for correlation function and density of states, which I'm interested in. So that is a more or less standard observable, not observable function that you're interested in. And another function, which is probably not so standard, but extremely useful for supersymmetry technique, is a correlation function of characteristic polynomials. So you consider the product of two determinant, and consider an expectation like that. And in principle, you can see that is not a, so correlation function is a local object. It has only says you about the behavior of finite number of eigenvalues. This function is global in general because you have a determinant, so you compute all kind of eigenvalues here and take the expectation over them. But the interesting thing is that objects are not only useful for supersymmetry, but it also is expected, and now it's proven, to have the same crossover point. So it's also expected that its behavior change if w cross square root of n. So it's expected that if w bigger than square root of n, we have GE behavior. If w smaller than square root of n, we have not Poisson, just one and another behavior. And in the middle, we also have some kind of behavior. So yes.
Just ask about the spectral correlation function.
Mm-hmm.
So is it true that from this, if you have enough information on this, down to small scales in eta, I guess?
Yes.
Then you can extract information about the
yes, the only thing that you need to take this z, there is no epsilon, so psi here is a complex thing like that. So what you need to take imaginary part of this z1 and z2 of different size. So one should be plus I epsilon, second should be minus I epsilon, and then it gives you information about the local statistics on this. So if you know enough information about that function, you can obtain the local statistics of. So you can obtain the bounds on Green's function square with absolute value. That is what typically people looking about to have this.
It's kind of like a generating function for all velocity sets, right?
Right, sure.
Yes.
So
but I'm wondering about the traces. I mean, I'm wondering how much averaging is in the definition.
So
and if you can get the sign kernel later and so on.
So it's not like a correlation function. To obtain a correlation function, you need to construct actually 4 of such kind of thing. But that trace is just a Stieltjes transform somehow. So what you have, yeah. So and from Stieltjes transform, you can extract the information about the measure. Okay, so now let me show what kind of integral representation you get. So the simplest case that you can obtain is a characteristic polynomial. So once again, you consider this average of 2 polynomials, and that is integral representation you can get by, once again, the standard algebraic manipulation. You can see that there is no Grassmann variables here. So X here is just 2 by 2 matrices, and J is a band profile that we have previously. So J is just some known function which is given in the model. So what you have here is just sum of trace xj xk, and that is actually what is somehow interaction in statistical mechanics model. And you have the product of determinant, which is somehow an external field. You may think about that as external field, or if you know how classical statistical mechanical models looks like. Okay, so you can see that here you have just a usual integral. Xj is 2 by 2 matrices, so the only problem that is you have quite variables, because each x have 4 variables, and so since you have n variables, what you get is 4n variables, and so n grows together with, so the number of variables grows together with volume. Actually, for density of states and for correlation function, so for this generalized correlation function, you get something which looks very similar. The only difference that except of x usual 2 by 2 Hermitian matrices, you obtain something which is called a super matrices. For the density of states, you have just 2 by 2 super matrices, which means that you have matrices like that. So Aj here is the usual variables complex, and rho j and tau j are Grassmann variables, so they are anti-commuting variables. And except trace and determinant, you have so-called super trace and super determinant. So you can actually, on this set of super matrices, you can define all kind of linear algebra, and then you have the same properties that you have with usual trace and determinant. So everything will be very, very similar, except you have not only just 2 by 2 matrices, but you have usual matrices, you have super matrices. For second correlation function, you have the same structure, but this Aj, rho j, Bj, and tau j will be 2 by 2 matrices. So Xj is 4 by 4 matrices with 2 blocks 2 by 2 usual matrices, and rho j and tau j are 2 by 2 Grassmann matrices. So you have in this, each matrix have 8 Grassmann variables. That is what we have generally.
Can I just interrupt for a second and just try to point out that with the choice of j's you made, those are nearest neighbor, j and k.
Yes, I'm going to show this in the next slide. Yes. So once again, that formula is true for any j and any kind of dimensional. You can d equal 2, d equal 3, it doesn't matter what you have. The problem is that you need to analyze this formula, and the simplest way to do is to take J inverse to be 3-diagonal matrix. That's why we choose such a strange choice of J. You can see that if we put J of this form that we discussed previously, then this J inverse that we have here will be just 3-diagonal matrix, and with a big parameter W that you have. That is first thing that I want to say. And so what you get really will be the nearest neighbor model. So what you get here, just j and j plus 1. Okay? And that's the first thing that I want to say. And second thing that I want to say about this thing, that if you take j like this and diagonalize xj by unitary transformation as usual, and then pretend that we can integrate over the so-called fast variables, which here is the eigenvalues. So mathematically that means that you take this formula, diagonalize xj by unitary matrices, and then put eigenvalues equal to their saddle point values. Just formally put, not prove that it's true, just formally put in them equal to their saddle point values. Then the interesting thing here is that what you get from that model will be a classical Heisenberg model. So because the saddle points of Aj and Bj is somehow 1 and minus 1 times some constant. So what you get here will be just, since Uj is 2 by 2 unitary matrix, this will be a vector on a unit sphere. And what you get will be the following. So you have Sj minus 1 is just vectors on the unit sphere. That's interaction, that is what is typically inverse temperature, is called beta. Yes, so here it's proportional to W square, and that is what you have, what kind of external field you have here so you multiply this Sj by the matrix which has 1 minus 1 on the diagonal, and that is what you have. So you really have the classical Heisenberg model with the complex external field, but the field is complex, but it's very, very small because it has 1 over n here. Yeah, so it's quite a tiny field that you have.
D equals 1?
Sorry?
Any D equals 1?
Yes, that is D equal 1, yes. But that, again, that is true for any dimension. You just obtain two-dimensional Heisenberg or three-dimensional Heisenberg. It doesn't matter.
And the integral becomes explicit also?
Yes, yes. So that is model. That is what you have if you formally put your eigenvalues equal to saddle points. So certainly mathematically you need to prove this, and that is main challenge. But after that you obtain just Heisenberg model, and from here it's easy to understand why you can have this sign kernel, because if your volume is small, so your spin ordered, then this is 0, yes, because scalar product of two ordered vector minus 1 is 0, and what you get is just the integral over, so your Sj are all equal, and what you get will be just the integral over 1 S0, and that integral gives you sign kernel, because that is the integral over a unitary group, which really gives you like that.
It's a giant saddle point method.
Yeah. Yeah, so from here you really can see the answer. And that, once again, that is true. You can see the answer for any dimensional. The hardest thing is to prove that you can do this for any dimensional. Okay, so let me now state this result for characteristic polynomials. The result is the following. So assume that we consider the characteristic function of the correlation function of characteristic polynomial, and we normalize it by some constant. Then the result is the following. If size of the matrix tends to infinity, we can have three different behaviors. The first behavior, if W is bigger than square root of n, gives you sign kernel, which is the same as you obtain for Gaussian case. If W is smaller than square root of n, then this limit will be just 1. And in between of them, what you get, so if n is proportional to W square, what you get is the following thing. So you have exponent of the spherical Laplacian plus some complex potential, that its complex potential is dependent on psi, and this nu is just this function. That is what you get here. So once again, Laplace operator, that is spherical Laplacian, so x is u12 square, that is a formula for each. This nu is some fixed function that we have, and that is what you have here. So T star is just some constant depending on density, and C star is a constant which comes from here. Yes?
Sorry to come back to this. I'm wondering what kind of information on the level of the eigenvalues does the characteristic polynomial tell you? I mean,
actually, not much.
Okay.
Yeah. So you can't obtain anything about localization or delocalization from that result. But the interesting thing is that you still have a crossover.
And it's the same as
Right.
Yes, yes.
It's pretty much the same.
Yeah.
Except you're.
Yeah. So once again, from here, what you can see. So.
Is that a heat kernel you have there? I mean, is that the heat kernel of that operator?
Yes, yes, that is heat kernel.
Okay.
Exactly.
So the heat kernel of that operator.
Of that Laplace plus IXC is this. Yes, yes, that is exactly what you have.
And is it? And then you have a C plus.
So what is so you have IXC nu star, where nu hat means that function operator of multiplication by that function.
Okay.
So what you get?
And you're applying that to the
to 1. Yes, exactly.
This is all taking place on the sphere.
Yes, yes. So this scalar product is on the sphere.
Functions on the sphere.
Yeah, yeah. Exactly. So you can see from here. You can see. So if C star is big, so U in the regime where W is smaller than square root of n, then if C star is big, Z is dominant term. Yes. and so you can forget about this. And if you apply exponent heat kernel of the Laplacian this to 1, you get just 1. Yes, that is what you give this. If C star is small, so you in this regime, then you can forget about the Laplacian, and what you get is exponent of this operator multiplied by 1 and then by 1 and then integrate it out. If you integrate this out, you obtain this sine kernel. That's how you can see. So from this result, you can really see both sides of that. Again, so probably I should say a few words about, so this was obtained even without, in 2013, without transfer matrices, just with pure spectral analysis, not spectral, pure set of point analysis, and two other result was obtained by transfer matrix approach. In principle, the first result you can also prove by the transfer matrix approach, but first it was proved by another technique. So you can see that about characteristic polynomial we know almost everything possible. So certainly there are some, you can see that here is 1/2 plus theta, not just bigger than so, but it's still not much what you can do here. Okay, so what is known about more characteristics that is more spectral characteristic somehow and can say you something about local behavior. So about the density of states first, it is known from the paper of Tom and Margaret and Princeton that that kind of bound. So that means that actually the expectation, the average density of states is minus the average density of states that we obtain for semicircle, that is CTS transform of semicircle, is the difference between them is bounded by C over W square in 3D, and that was also obtained by supersymmetry, but the method which was used for analysis of that is a cluster expansion. By the same technique, later it was obtained in 2D, and by transfer matrix approach, but again using the supersymmetry representation, we obtain this in 1D case by the transfer matrix approach. So
in these cases you can allow the imaginary part to be much smaller.
Yes, yes. So the problems here, you really can take imaginary part here as small as you wish, but the problem is that you have average here. So that kind of inequality does not have, can give you information about delocalization. The only thing that you can say is some kind of smoothness of density or something like that, but not information about delocalization. The results which was with the imaginary part of the of order 1 over W, they can prove something without this expectation. And but that result, in principle, they can take epsilon of order smaller than 1 over W, but they, on that scale, they can say you something about localization or delocalization. So the works that I cited previously by Erdős, Yao, Knowles, and some other people, they really prove some kind of local semicircle law, but without average. And that kind of laws give them information, not information about the strong form of delocalization, but some kind of information about delocalization on this scale. Okay, so what about the full model? About the full model, again, there are some results on supersymmetric basis, and again, here we consider these block band matrices, not the matrices with decay in J, just these block matrices, and then again for W of order n, we can prove that is usual correlation function, and that goes to the determinant of the sine kernel. And that is true is a finite, so W proportional to n means that you consider this matrix with a finite number of blocks. And with a finite number of blocks, you can consider it in any dimensional, and you have the sine kernel. So after that paper in 2015, there was obtained another result which does not deal with the correlation function. It was concentrated on delocalization, but it was proved that delocalization length is bigger than W7/6, and this is a strong form of delocalization. So here they really can control the Green's function up to the order 1/n. Not 1/w, but 1/n. But only with this n bigger than w to the 7, w bigger than n to 6/7. And that paper used the technique that was developed here, but they can do, as I told you, with the standard approach, they can do this for not only for Gaussian distribution, but also for distribution with sub-Gaussian tail and for Gaussian moments.
But they also use the supersymmetry?
Yes, yes, exactly.
I mean, it basically follows what you're
Yes, yes. Okay, so now let me state another result. So I told you what is the sigma modular approximation for the characteristic polynomial. Another interesting thing is what is somehow of sigma modular approximation for correlation function. That is a recent result that we get with Maria Shcherbina, and the result states the following. So first of all, what we did, we consider this 3-block diagonal matrix and consider so J is like here, yes, and take this alpha that we have here off, rescale it and put alpha over W square here. Then we, using the proper limit transition, we can obtain fix beta and n, and so beta is this coefficient that we have here, and then we put W to infinity. That gives something which is physicists typically consider in the very beginning of this model. Yeah, we rescale that and consider the limit W goes to infinity, and that gives you so-called sigma modular approximation of correlation function. So as you can see, again, you have here some kind of statistical mechanics model. This is super trace, means some kind of trace, but for super matrices. And matrices that you have here now are not 2x2 complex matrices, is just a super matrices of the following form. So it looks a little bit complicated, yes, but generally it's not so bad. So what you have here, this is 2x2 unitary matrix, Sj is 2x2 hyperbolic matrices, so that is usual matrices, complex matrices, and in the middle you have Grassmannian part, so anti-commutant part, and that part has 4 Grassmann variables. So this matrix tau j hat and rho j hat, they are diagonal matrix which has 2 independent Grassmann on the diagonal. So this is diagonal matrix, this is diagonal matrix, and here you have product of these Grassmann variables times matrix L, where L is just 1 minus 1. So you can see that if you compute qj square, that will be 1. And that type of model was obtained first by Febuary, but that was a physical paper which is not rigorous. So, but it looks really very, very similar to what we have here. And this computation is completely rigorous. So we can also obtain some kind of sigma model, but that sigma model is slightly different from the Yefetov's one, but it has all qualitative properties that Yefetov's model has. That is the main point. So it's very, very similar to what we have. And once again, what we have is classical Gibbs measure. So we have here some kind of beta with some kind of interaction. We have an external, small external field here. This lambda is a matrix with 1 minus 1, 1 minus 1 on the diagonal. So it's some fixed matrix. Yes. So physicists typically consider that kind of sigma modular approximation because they believe that this kind of approximation has all qualitative physics that in the model, because it has the same type of symmetry and people expect that they have the same properties. And here it's really true, because so what is in this problem, there is two such kinds of different problems. First is to derive the sigma model approximation rigorously, and second is to analyze the sigma model approximation rigorously. So to derive it, you need to do just this rescaling and one limit. To analyze it, you need to understand what should be the crossover point. Here the crossover point should be beta of order n. So it's expected that if beta of bigger than volume, you have one behavior, which is GE behavior. If beta of smaller than n, you should have Poisson behavior. So our result that indeed, if beta bigger than n, you have GE statistics. And that result, unfortunately, not for the whole bulk of the spectrum. You have energy smaller than square root of 2, but that is technical condition which comes from that we don't really want to deform the contours properly. So in principle, I think it should be avoided, but again, it's already quite complicated. Yes, yes. Yeah, so what we can prove that if we have this model with rescaling, and if we first put W to infinity, and then put beta and n to infinity with order like this, so beta is bigger than n times log square of n, then we get the behavior that we have for GUE matrices, so 1 minus sign kernel. So let me remind you that if you want, so that is actually what we want to obtain for the correlation function. Unfortunately, we want to obtain it not in these limits, because to obtain the really, to prove universality for this kind of band matrices, what you really need to do, you need to take beta, rescale it back to alpha, and then you need fix alpha and put W and n together to infinity. So here what we did, we put first W to infinity and then beta and n to infinity. What we need to obtain universality for the band matrices, not in sigma model approximation, just the usual universality, how people from random matrix point of view think about that. You need to put W and n both to infinity, and W should be bigger than n. That is what we expect to have. Unfortunately, that limit is much harder. But in principle, we expect that, and physicists also expect so, that all kind of structures that we have here should be, so the result and the structure should be very similar to what we have here. Of the full model should be similar to what we have here. So in principle, you can see, so what is the matrix here? You can see that it's also 4x4 supermatrix. In the full model, you also have 4x4 supermatrix. But here you have just 4 Grassmanns, because you have 2 diagonal matrix with independent Grassmanns, yes. But in the full model, you have 8 Grassmanns. The density has just 2 Grassmanns. Yeah.
So what would it mean to take W to infinity before n? Because,
that's why I need to rescale, because in the if you don't rescale, you can't do it like that. So actually, what means first limit actually means the following: I fix the volume, and then I do the integrate out the eigenvalues somehow. So that after rescaling, that limit W goes to infinity means that actually I don't touch the continuous symmetry, I just integrate out the eigenvalues. How it was in the model with determinant. So,
well, I mean, I guess you can do it in the sigma model, but if you go back to the matrices, it doesn't make sense, right? Or
so that is why I can't do it right. Right. Yes, I need. So to obtain the sigma model from my matrix, I need to some proper rescaling.
Maybe the question
yes.
is also, what is little n in the matrix?
Little n is the same as big n. Okay. Sorry. So that is the size of the matrix. So here is probably the number of blocks. Actually, yes, the number of blocks. The true things, because the size is n over w times w. So that's a kind of so to deal with the real model. Certainly, I can't just take w to infinity. It doesn't make any sense. So that is why to obtain some kind of sigma modular approximation, I need some kind of rescaling. But the interesting thing that we believe, and physicists also believe in this, that this simpler limit should have the same property as the big model that we have. So certainly I simplify my life. I do it in
you can just say this is the model you want to study.
Yes.
And this is the standard, more or less the standard.
Yes, yes. But I want to, since
so what you've done is you've taken the regular sigma model, but you've frozen the saddle eigenvalue.
Yes, exactly.
That's it.
Yes.
And then everything's okay, right? Then,
yes, that is what I want to.
Right. So you only use that as a way of justifying the fact that you're choosing a saddle energy.
Yes, so somehow that is just, so since I'm a mathematician, and I would prefer to have some rigorous computation to obtain that kind of sigma model approximation. The effect of computation is non-rigorous. That's why I want to do something, so to obtain this from some real matrix ensemble. And that is ensemble, I can take that just 3 diagonal with fixed dispersion, but I can rescale it a little bit, and after that I can obtain sigma model, which should give me information about the big model. So it's not completely probably clear why after this rescale should give me the right information, but that's somehow a trick how I can get it. So, roughly speaking, Tom is right. What I can do, I can just say that that is my model. But I just want to say that that model is connected with models that we considered previously by that scaling and limit.
And you might also want to say that if you go back to the one that you were discussing earlier, and the Q's are replaced by S's or points in the sphere,
yeah.
and you're back to the...
Yes, you get back the Heisenberg model. So what you get? Yeah, so somehow that is again statistical mechanics model, but your spin's now not on the sphere, but on some supermanifold. And so it's harder to analyze. But the good thing here that it's... so for the full model, you obtain something very similar, except that matrix will be a little bit more difficult than you have. So it has 4 Grassmann variables, matrix that for the full model has 8 Grassmann variables, but and also has more real variables that you need to consider, but anyway it's quite close to what you get. So once again, that model can give you real information about the eigenvalues of the full model. That's just some approximation. That's only what you can do. We expect that so we first do it for characteristic polynomials, then for density of states, and then for this kind of sigma model. So we expect that it allows us to develop the technique to such extent that we can do it with full model. So that was like an intermediate step, only like that. Okay, so what I have to say probably that, as I told you, that is part of the big project, and that project is use a transfer matrix approach to all that kind of spectral characteristic. So transfer matrix approach based on that if you have nearest neighbor model, you can write your integral representation as an iteration of some operator, and you can consider the spectral characteristic of this operator. So, for example, for characteristic polynomials with this covariance, just to give you an idea what kind of operator you get, looks like that. So you have a difference between difference operator like that, and you have a function multiplication by function f, which is just some kind of function of x. So this operator is in principle it's quite nice. The only problem that is it's not self-adjoint. So standard spectral methods does not work properly, so you need to be very careful with it. That is the first problem. Second problem is that for characteristic polynomials it's quite nice. So X is just 2 by 2 Hermitian matrix and so on. If you want to deal with density of states or correlation functions, this X will be 2 by 2 matrix with Grassmann variables or 4 by 4 matrix with 8 Grassmann variables. And the main problem that means that actually these kernels that you have, so your kernel of your transfer operator, here it's just a scalar function, but if you, for characteristic polynomial, if you're interested in, for example, second correlation function, that will be 256 times 256 matrix. And even if you use the symmetry of the problem, you can reduce the size of this matrix, but it still will be 70 by 70. And so it's quite complicated structure, and you need to deal with this structure. So we believe that the main block and main contribution of this matrix again will be 4 by 4, as it was for sigma modular approximation. But
so this, I don't, you probably said it, but I didn't quite understand. So you're acting on L2?
Yes, so for characteristic polynomials and just L2 on Hermitian set of Hermitian matrices.
Yes.
For if you're interested in density of states,
Yes.
that will be 4 by tensor product of 4 such spaces. Because
direct sum.
direct sum of
of
4 such
so
spaces.
it's a vector L.
Yes, it's even not a vector, it's a matrix.
Okay.
Yes, it's vector. If you're interested, it will be the matrix, because so in principle you can consider still it's in some Grassmann space, but to be more careful with what you do, and I prefer to have some kind of real spaces or complex spaces. Yeah.
You do this for d equal 1 or for all dimensions?
No, only for d equal 1. The main problem that transfer matrix approach you can apply only for nearest neighbor model and only for the chain. So you can't do anything in 2D. Yes, but it's hard. So, but in principle, transfer matrix approach is more appropriate for 1D case. Probably in 2D it's possible to do something in a strip, but again that can be complicated. Yeah, so, and the third problem that I probably also have to say, that you have a continuous symmetry here. So it's not like, so this X, it's symmetric on the unitary group. If you have a bigger matrix, it's symmetric over some bigger space, which involves symmetry on the sphere and symmetry on the hyperbolic group. So you need to deal with a special function that acts on the spherical harmonics or hyperbolic harmonics, something like that.
Have to deal with those?
Yes, we need them, and we need some property of them.
So, but then these subspaces are left invariant.
Yes, but
Then I guess it broke.
it's broken because of f that you have here. So if you have this model that we discussed with just 2,
So then that
but if you have f for all stuff like that, so if you have this xi for all sides, you need to deal with them somehow.
Well, already these problems are hiring out. I mean, once you set this thing up, is all the work then really boils down to understanding these?
Yes. Even here it's
just the interval. Just this interval operator.
Yes, it's true. So you can see that in principle, so we know how to deal with the first problem because the operator is not so far drawn even on the stage of characteristic polynomial. The complicated symmetry is already exists in sigma model approximation, and the only thing that we don't know how to deal with now is the big size and complex structure of this matrix. So we can do it with, so for sigma modular approximation you need to deal with 6 by 6 matrix actually, but it's a little bit less than 70 by 70.
But if you don't have you can also use a transfer matrix, right, without sigma model approximation.
Yes, sure, you can. You can, but that's what you have. Your operator will be a big matrix with whose elements are operator on L2 on Hermitian matrix. So you have a big matrix like 256 times 256, and each element of this matrix will be some operator on L2 on Hermitian matrix. Hermitian and hyperbolic.
Operator L2.
Yes, yes. So for characteristic polynomial, you just have L2, one L2. For density of states, you have 2 by 2, so matrices.
And then can you intuitively see which sectors are the important?
Yes, yes, I can, but I can't prove this.
And then are you off to the top eigenvalue?
Yes, so the problem that you need to write this as a product, tensor product of 4 2 by 2 matrices somehow. 2 of them gives you the top eigenvalues, and 2 of them is a Jordan cell, so you need to deal a little bit with them, but certainly the main thing that you take a top eigenvalues there, and the next eigenvalue should give you the spectral gap 1 over W square. We expect to have this, and we even can see this on sigma model.
So in a sigma model?
Yes, in a sigma model you can prove this. Yes, again, but that gap we can do only if beta bigger than n. So the computation depends on beta.
In a sigma model approximation, you get the right gap.
Yes, I think so. Yes, that in sigma model approximation we can do this. Yes.
Is there a unique top eigenvector?
Here, yes, yes, it's unique. Okay, so that's probably all what I want to say, so thank you for your attention.
We've had a lot of questions already, but maybe some more.
I mean, I guess you had this result in the intermediate scale for the characteristic polynomial, for the E-kernel.
Yeah.
But in the very beginning, you talked about the conjectures. There was no conjecture on the intermediate scale, is there?
Actually, there are some conjectures what will be happening in the middle of, so near the crossover, but it's quite hard to explain. So it's expected that you have something like multifractality there, because Schrödinger has something like that. But actually nobody can prove anything, and even supersymmetric calculation. So that conjecture that I have with, that I wrote here, in the very beginning, where is that? Let me, this one. This conjecture in D equal 1 was obtained by some very rude supersymmetric computation by Fyodorov and Mirlin, but they don't know how to compute it in a proper way in the middle. So there are some conjecture what will be the correlation function there, that it doesn't depend on scale. So, but anyway, there's no something that you can really write like a conjecture there.
So is there a multifractal behavior in 2 dimensions? Is that?
I don't even know if people were.
You formulate a question where, I mean, you do have kind of crossover, right?
Yes, yes, we expect to have.
You see the multifractal structure.
I think that people so far from thinking of that, because you really. Yeah, Fyodorov thinks that probably there will be something like that, yes, but he can explain what.
The eigenfunctions would look they wouldn't be localized, they wouldn't be extended.
Yes, and they should.
That would be something in between.
Something in between, but what exactly that will be, I think that he doesn't know actually. So it's people expect that there will be also some multiple-fractality there, probably, as far as I understand. They consider these band matrices with this kind of thing. Yes, this is power law, but as far as I know, they can do even compute something in 2D. No. They can only have some kind of computation in 1D, and even this computation are far from real strong conjecture.
But you have a result on the intermediate scale in 1D. I mean, is there anything multifractal about your...
No, that is a different thing, because that actually, as I told you, characteristic polynomials, it's not the local statistic.
Yeah.
It can really gives you information about eigenstates. It gives you just some information here, and multifractality or something like that, it's information about how the spectral function looks like. So characteristic polynomial can't say you such kind of thing. So it's a nice result because you can really see what happens with characteristic polynomials there, but it doesn't have anything like that here.
Okay, thank you very much.